Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to introduce you guys to actually three more really important trig functions. They're actually called the reciprocal trig functions, and I'll show you what I mean by that and everything. But to get started, I want to do this problem. So this is kind of the opposite of what we did in the last video. So in the last video, right, we found, given an angle, right, we could do things where we find the tangent of some angle is like some number, right, some like ratio of the sides of a right triangle. But now we're told the ratio, and we want to get the angle in here, okay? And there actually is inverse trig function, so you could do it this way. So you define the inverse of tangent just that way. That's how we write it. That's just the inverse tangent function. And we will talk about some of these. So one way you can just do it is, you know, if you take tan inverse of tan of x, tan inverse of negative root 3, you know, these truly cancel each other out. You get x equals inverse tangent of negative root 3, and you could use your calculator to get, you know, what angle that is. But we're going to do it just utilizing unit circles, so I don't want to actually do it this way yet. We will talk about inverse trig functions, but not yet. And just to be clear too, there is such a thing as inverse sine, and inverse cosine. And you just write it with that little -1 that we're used to with inverse functions. But again, not quite ready for that yet. So to do this, I'm going to go back to unit circle. So we know tangent is negative, right? And so with my all students take calc thing, the answer is negative, so I can't be in that quadrant, right? And I also can't be in that quadrant, right? Because tangent's positive there. So I know I'm in quadrants 2 or 4, right? And to do this, you know, basically what I would do is just do that finger trick kind of thing in that last video. So, you know, tangent of x is just defined this way. Right, square root of finger is below over square root of finger is above, and that really just comes because, you know, tangent is just sine of x over cosine of x, something that, you know, hopefully you know from geometry as well. And so I would basically just use the finger trick. So, you know, it's hard to show you, but literally I have my hand out, and I'm just thinking, when do I have, you know, 3 fingers below an angle, and when, you know, do I have 1 above, right? Because this tangent of x equals negative root 3 over, you know, square root of 1. There's like a 1 in there, right? And so that's like my pointer finger. And so that is what's like equivalent to kind of 60 degrees. But we don't want 60 degrees, right? Because we don't want to be in that quadrant, but we can just do a 60-degree reference angle in these 2 quadrants, right? So actually, let me get rid of the one I don't want. And so I could have 60 there, and then I could have 60 there. And then you've got it, right? Because you either have, let's see, so you have this angle, right? Or you have that angle. And so x could either be 120, right? 90 plus 30. And then, or x, we'll call it x1, x2, could also be, you could describe it, I guess, 2 ways. You could either describe it as negative 60, right? Or you could describe it as 300, so it doesn't really matter. But you got to be careful, because in these problems, there was no information given about what quadrant you're in. And so both of those are definitely answers, but there's even more answers, because I could also, right, I could go to this angle, but I could also rotate around 360 more degrees, or I could rotate around another 360, or another one, or another one, or another one, right? And so the way we actually write this answer is we write plus 360n, and n is just like a multiplier, like 1, 2, 3, so on and so on and so on. And same thing here, right? I could rotate around and around and around the circle. And so that's actually the correct answer. But you could also write it in radians, right? You can either have, so 120 is 2 pi over 3. And so then for that one, you would add 2 pi plus n. Or you could say negative like pi over 3, let's do, because negative like 60, right? Plus 2 pi n. So I don't care really how you write it. You can either write it that way or that way. You will see this more in like pre-calc and calc and everything else after that. But both of these are technically fine. So any x that satisfies this kind of thing would make the tangent of that would be negative root 3. All right, so the main plan, like I said today, is talk about these things called reciprocal trig functions. So there are 3 more trig functions that you need to know, and they still are defined in terms of a right triangle. So let me actually draw a right triangle here. There we go. So let's take that as my angle, and basically from that angle, right, we have the opposite side here, the hypotenuse here, and the adjacent side here. And so they look kind of weird. So one of them is called secant, okay? And secant is like an actual geometric thing, and there's actually a reason it has that name, but I don't want to get into all that right now. And just like sine, cosine, tangent, this thing has an abbreviation. It's SEC, so we can take like SET of theta. And what this is defined as is actually the hypotenuse over the adjacent side. So it's H over A, right? You also have something called cosecant, okay? There's co-functions for secant, just like there's cosine functions too. And this one gets the abbreviation CSC, and this is going to be the hypotenuse over the opposite side. Right? And then there's something called cotangent. Right? And cotangent gets the abbreviation COT. Pretty nice one. And that one's just going to be adjacent over the opposite side. And instead of really remembering all of this, to be honest, they're reciprocal trig functions, and they're easy to remember if you just realize actually a connection between the ratio of these sides and something we already know. So if you look, take sine of theta, right? Sine is this over this, right? Opposite over hypotenuse, which is basically the flip of that, okay? And truly, cosecant of theta is 1 over sine of theta, right? And since cosine of theta is adjacent over hypotenuse, notice that secant of theta is 1 over cosine of theta. And last but not least, since tangent of theta is opposite over adjacent, notice that cotangent of theta is actually just 1 over the tangent of theta. And so this is exactly what it means to be reciprocal, right? And so that's where they get their name. They're the reciprocal trig functions because the way you can remember these is just doing 1 over their corresponding trig function. And this one, a lot of times students are fine with because, tangent and cotangent go together like that. But this can be a little hard to remember, these two right here. And this is kind of what I always tell students. The first letters need to be different. Notice that they're not starting off with the same letter. C, S, S, C, right? So if you're having a hard time remembering, is cosecant the reciprocal to sine or cosine? It's just the other letter, right? So cosecant starts with a C. It's reciprocal to sine. Starts with an S. Secant starts with an S. Must be reciprocal to cosine, okay? I didn't come up with it. It's just what it is. I wish maybe that they really were the same letter, but that's not what it is. But you do need to definitely know these. They're very, very, very common trig functions. We will actually graph them and all sorts of things with them. For the homework for this video, we will be doing stuff kind of like this. So without getting into like inverse functions and things like that, we can, given this and without a calculator, we can basically just use what we know about unit circle and stuff and find what x is, given that x terminates in quadrant 3, okay? So probably the first thing I do is just simplify this a little bit, okay? Divide by that 3 root 3. Cotangent of x would then equal 1 over root 3. But we know, right, I just told you, that cotangent is 1 over tangent. So if I just do the reciprocal, both sides here, flip this around, then I'd have to flip this around, right? That would say that tangent of x is root 3, okay? And so now we basically just go to kind of like back to kind of what we did in this sort of problem, right? I know I'm in quadrant 3, okay, over here. It's a bad line. And that all checks out, right, with the all students take calc thing because tangent is positive down there. There would have been an angle in the first quadrant too that would get me root 3, but we're just concerned with that one. And we kind of already did this problem because we know that for the same reason, with this argument with the square root of fingers below over square root of fingers above, we know that the reference angle is like a 60. So I'm going to just draw like a 60 degree in there. And so we're really concerned with that angle. And so it would basically be, let's do it actually in radians. I want to get you kind of used to radians. So, here is 1 pi over 3. Here is 2 pi over 3. Here's 3 pi over 3. And here's 4 pi over 3. So there's sort of 4 60s, right? 60, 120, 180, plus another 60, right? So 1, 2, 3, 4 pi over 3s. So x equals 4 pi over 3. And again, we can keep cycling, right? To get back to quadrant 3, we can go another 2 pi, or another 2 pi, or another 2 pi. So I'm going to add to that 2 pi n again. And you don't really have to write this every time, but I'm just doing it right now. But n is just one of these. It's actually just what we call a natural number. It's one of the number sets. That'd be it. So that would be the answer in radians. Okay, so 4 pi over 3 plus 2 pi n. Anything like that would get me, would solve this equation that I started with up here. All right, I just want to go through a few of the other directions of these problems. So we've done a few now where we solved for x, but now I want to give it an angle, get what the ratio of the sides is. So basically for any of these problems, I just personally, I still to this day use that finger trick to kind of figure out what the exact value of these things are. So, and I'll kind of go through a few little ideas of like how I can use a few other kinds of tricks to help me. Like specifically, I'm thinking of one down here in this problem. But it is kind of a hard thing to show in a video. There's not a lot of work to show, and it's kind of just honestly counted out on my hand, so it's not the easiest thing but to show in a video. But this is kind of how I think about it. So first, I think about what quadrant I'm in, right? So 330 is going to be way over here, right? That's going to be a 30 degree in there, right? That's my reference angle. You always make it, right, with the x-axis, the 90 degree. And so then I literally just go to I use my left hand because I'm writing with my right, and 30 degrees is like my ring finger, and then it's just for tangent, square root of fingers above, square root of fingers below over square root of fingers above, which in this case, right, is just going to be equal to square root of 1 over square root of 3. And then the only thing you got to think about also is the all students take calc thing. So we can see that only cosine's positive there, so it's negative. And of course, we don't really need the square root of 1. So that's all you got to do for tangent, okay? Let's move on to secant. So the way I would do this, I would really think about it as 1 over cosine. Remember the first few letters need to alternate. So it's 1 over cosine of 120. And I would just solve cosine 120, and then I'll just take the reciprocal in my answer, okay? So here, 120 is right there, right? And that would give me a 60-degree reference angle in there. And for cosine, right, it's just square root of fingers above over 2. And so in this case, there's only 1 finger above, so it's going to be 1 over 2. And then, again, all students take calc. Sine's positive, cosine's not, so we would get 1 over negative 1/2, otherwise known as negative 2. So that would be the answer for that one. Cosecant, basically just do 1 over sine of 2 pi over 3. And so 2 pi over 3 is actually also 120. And so this is 2 pi over 3. And so it leaves me with another pi over 3 to get to 3 pi over 3, or pi. And sine, you're just going to go the other kind of direction. So it would be 1 over square root of 3 over 2, right? There's 3 fingers below your pointer finger there, and always over 2 for the sines and cosines. And same thing, all students take calc. It's positive, so I can just write it 2 over root 3, and that's it. The last one here, you can definitely think of this as 1 over tangent, right, of 11 pi over 4. And the nice thing with the over 4s, this is like a different trick that I haven't really talked about yet, but pi over 4 is 45, and so there's going to be a pi over 4 there, then there's another one there, then there's another one halfway there. Well, that wasn't that good of a halfway. So there's another one there, another one there, and another one there, another one there, right? And so pi over 4s are really easy to count off because they're just right in the middle. So if you want to count 11 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So that the triangle I have is right here. And the reference angle for a pi over 4 is always, like any multiple of a pi over 4, is always pi over 4. And these are your nice equilateral triangles. Well, not equilateral, sorry, isosceles triangles. Those two are the same length, they'll have 2 legs of the triangle. And so tangent, since it's a ratio of the legs, right, opposite over adjacent, they're the same length, so you'll actually get a 1, right? So you get a 1 over 1, and then you just got to do again. All students take calc. Sine's positive here, tangent's not sine, so put a negative on there, and then you might as well just write it as negative 1. So I'm still explaining a lot, but honestly, like when you get good at this, you can kind of do all 4 of these probably in under a minute. Like it's really pretty quick. And a lot of it's done counting off on your hand. So that's kind of a very, very, very quick kind of problem, honestly, down the road. And you really want to be quick at it because evaluating these things will become a very important part of a lot of other problems. So one other thing I just wanted to show you here is like a trick that we can also use involving the symmetry of the unit circle to help evaluate what sine, cosine stuff equal, or also to work backwards on problems like this. So the symmetry trick actually has its roots due to something that has to do with a term called even or odd functions, right? So we know that like cubics are odd functions, right? We studied these a bunch earlier in this year, like really x to the fifth or x to the seventh, all those things kind of look like that. Quadratics, quartics, x to the fourth, all of those things are even, right? Well, it turns out that sine and cosine are also, one of them's even, one of them's odd, and it'll make a little more sense when we graph them, but sine looks like this, kind of, and there's actually some symmetry along a diagonal here, just the same way this is symmetric along a diagonal, and across the origin, really. And so sine is actually a odd function, and if you, when you will, graph cosine, cosine kind of looks like this, and it just kind of keeps going. And you can see how it's like symmetric with the y-axis, and that is actually one of the reasons why cosine is an even function, just like quadratics and stuff. But because of that, you get some nice symmetries and patterns in the unit circle. And so, like, say we wanted to know what x value gives, I can take the cosine out and get 1/2. If you can remember, this first quadrant, really, of your 30, 45, 60, and, definitely your 90 and your 0, too, these are the corresponding x and y values for those. But then you can just use symmetries and kind of flip things around. So this is what I mean. So cosine, right, we saw before that like x is equal to the cosine of theta, right? And we don't need it here, but y is equal to the sine of x, sorry. X is equal to cosine of x, y is equal to sine of x. We saw that in previous video. And so what we can do is we can be like, okay, well, where do I see a 1/2, right? And using symmetry, like an x equals 1/2, I can just flip that down, right? And I would have the other one, of course, down there. Fits really nicely with the all students take calc thing, right? Cosine's positive here. All trig functions are positive up there. And so then you can just use symmetry and get like your answer really fast, because you can kind of just utilize the fact that there's a lot of mirroring going on here in the unit circle. So, of course, this is 60, it's labeled right there, and then this is like minus 60. So minus 60 is 300, right? So x equals 60 or 300. And this notation, right, is just interval notation for, I just want answers between 0 and 2 pi. And I include the 0, but not the 2 pi. So I'm saying basically one full lap, right? Because 0 is equal to 2 pi. So that right there just literally represents start at 0, go through all these different angles, right? All these different angles. And then you get like infinitesimally close to 2 pi, but 2 pi is 0. So I'm saying how many solutions are there in the first lap on the circle? And it would just be those two, 60 and 300. And you can do the same thing for sine, but you would be flipping, the y values. So, notice here, you could flip over and get the same y value over here. If you were down here in this quadrant, you could flip over and get the same y value there. So for the symmetry part with sine, you just flip kind of left and right versus up and down for cosine. So that's just another little shortcut, but the finger trick thing is still by far one of the most useful things. All right, so just want to do a few, I think just two quick little problems I'll have time for here. So now that we know all 6 trig functions, I want to kind of revisit one of these. We did one of these problems before, but just for 3 trig functions. But if an angle terminates right here, and the x value is -1/2, and the y is -√3/2, this is a unit circle. Notice the ones, right? We can get all 6 trig functions without any work. So, sine of, I'll just call this angle x, actually. I think they called it t. I just noticed there's a t there. So sine of t is the y value, right? So -√3/2. Cosine of t is the x value, -1/2, right? So from those two, I can get cosecant and secant really quick. So cosecant is just the reciprocal of sine, so -2/√3. Secant is a reciprocal of cosine, so -2, right? And then for tangent, you would just do, sine over cosine. So sine of t over cosine of t. Or you can just do, of course, y over x, right? So it's just really the y value there over the x value. And so in that case, we would get √3. And so then cotangent of t would just be the reciprocal of that, which is 1/√3. So seems like maybe at first there's like a ton to do, but really a lot of this is pretty quick. And it's kind of like every time you get one of them, like sine, you in that sense also get cosecant, because you just got to remember which one it's reciprocal to, but then you just flip it around like that. Just similar problem, but now it's not necessarily a unit circle, okay? So there's no labels on this circle. It's just a circle. And it says if cosine of t equals 12/13, so notice it's the x value, right? And t is in quadrant 4, as shown here. Find the values of the other 5 trig functions, okay? So one that I'm kind of thinking we should just get first is secant. Secant is just a reciprocal of cosine, so it's 13/12, right? We don't need to do any more work for that one. That one's just done. To get any others, though, we're going to have to use kind of a trick here. So to get the next one I'm actually going to get is sine. So remember that I showed you in a previous video sine squared of any angle plus cosine squared of any angle is equal to 1. So we have cosine of this angle t, so we should be able to get sine from that, right? And that's kind of the trick here. So going and plugging in what I know, so I know cosine is 12/13, right? So I'm going to have to do 12/13 squared equals 1. And so then sine squared is equal to just 1 minus 144/169. So sine squared of theta is equal to 25/169, if you just do that out right there. And then that's really nice, because then sine of theta, these are both perfect squares, is equal to plus or minus 5/13. But, so really, actually I'm going to flip all these to t's. Sorry, they should have been t's. But we know we're over here, right? And if you just do the all students take calc thing, we know that sine should be negative there. So sine of t is -5/13. And then the rest of them will come really quickly here. So cosecant of t is -13/5, right? Tangent of t is just sine over cosine. So we would get -5/12, and then cotangent of t is just the reciprocal of that, so 12/-5. So 1, 2, 3, 4, and then 5, right? And if you don't use this, you're really kind of stumped. So you definitely want to remember this. It's a very, very, very useful identity that we're going to use time and time again.